Alright, so now we're back to finish out Chapter 10 and to finish out this semester. So, we ended up the last video starting to talk about hybrid orbitals and how if we had 4 hydrogens, there's not really 4 spots to put them for carbon, but yet carbon binds to 4 hydrogens. And so how does it do that? And so what we said is it makes a hybrid orbital between its s and p orbital, causing what's known as an sp3 orbital, which is what we saw here, to where now if we had 4 hydrogens, one can go there, one can go there, one can go there. And we learned in the previous video that anything bound to 4 electron groups is in a tetrahedral arrangement. And so sp3 leads to a tetrahedral arrangement. It's a complete hybridization of all the s's and p's. So, let's see if we can make a hybridization that's not complete between the s and the p. So let's look at carbon again. Carbon is 2s, 2p. Actually, I won't fill in the electrons this time. And so what we can also do is hybridize these together. And when we do that, we get 3 sp2 hybrid orbitals. So again, if the trick is to look at the number on the p to tell you how many of them have been hybridized. So we know you have to hybridize the s. If you don't hybridize the s, you can't get hybrid orbitals. So it has to be an s, and then like we saw last time, p3 was all 3 p orbitals. Here we're only doing 2, so it's going to be sp2. And then we have 1 p that's unhybridized. So what in the world are we going to do with this? How can we have a p orbital unhybridized? Or what does that tell us? This tells us that we're going to have a double bond. So, we have 1 electron, 1 electron, 1 electron, 1 electron. So, carbon uses these 2 to bind to oxygen, or to 2 hydrogens. It uses another one to bind to oxygen, but we know the Lewis structure also contains a double bond. So what in the world? Let's talk about the different types of bonds we can have. These bonds right here, the bonds that come about through binding through a hybrid sp orbital, these are known as sigma bonds. So since we saw oxygen binds once through an sp orbital, so one of these bonds is a sigma bond. Well, the other bond has to be something different, right? Because it binds to the unpaired or to the unhybrid p orbital. This is known as a pi bond. What we can think of pi bonds as double bonds as affecting the rotation. And so what I mean by that, for the purposes of this example, I want you to pretend that that the 2 middle carbons have an octet, even though that they don't. I want you to pretend. As drawn here, with just a single bond in the middle, would these 2 molecules be exactly the same? The correct answer is yes. Right? Because that single bond, those elements, those 2 carbons can spin on each other. And so those are the two same things. But if I add a double bond in there, those cannot spin freely. And so they're locked into position. So what we have is cis and trans, all because of the double bond. So we'll talk about what we can do with these different types of bonds and what I will ask you guys to do with them. But let's keep going on. So now we have 2s, 2p. So if we did 3 the first time, 2 the second time, we're only going to do 1 this time. So we're going to have sp1 in the middle with 2 unhybridized p orbitals. So if one unhybridized p orbital led to a double bond, what would 2 unhybridized p orbitals lead to? If you said a triple bond, you are correct. And I messed up. You should have 2 sp1 orbitals and 2 unhybridized p orbitals. So, again, the number of hybridized orbitals equals to the number on top, or sp. This is sp or sp1. The number on top plus the s, because you need to add the s, because we can't get rid of any orbitals. And so, if a bond comes from an sp orbital, it is known as a sigma bond. If a bond comes from an unhybridized p orbital, it is a pi bond. And so we have 2 pi's and a sigma. So, I forgot to mention, and I apologize, sp2 hybrid orbitals, trigonal planar. sp orbitals, as you can see from here, the C with a triple bond with another C, this is going to be linear. And we said sp3 is tetrahedral. So, do you think, and I'll just open this up to you, do you think that we can only hybridize s and p orbitals? If you said no, because I asked that question, that is correct. Plus, we can bind things to 6 different things, correct? And this is where we get expanded octets. This is the reason why we get expanded octets. So, now we have an S, P, and D. So we have an S, P, and D. So we can hybridize all of these together. So how many total hybrid orbitals will we have? Well, let's count. 1, 2, 3, 4, 5. So we're going to make 1, 2, 3, 5 new hybrid orbitals, and these are going to be S, P, 3, D. Right, again, we're just labeling what we're going to be using. And so sp3d, if we're bound to 5 different things, it's going to be trigonal pyramidal. Or bipyramidal, excuse me. Trigonal bipyramidal. So, did we stop at 5 though? No. So what we can do is add one more d orbital to the hybridization. And so here we're going to get 1, 2, 3, 4, 6. And these are sp3d2. And this goes for an octahedral arrangement. Again, the bond angles are the same as we saw before. So, hybrid orbitals. Why do we care about hybrid orbitals? Here's why we care. Or at least here's what I might have you do with them. Let's look at a molecule. Here's an organic molecule. And what I would do is I would ask you, for this carbon, what is the hybridization scheme, or what is the hybridization of that carbon molecule? Well, let's look at it. It's got 1, 2, 3, 4 bonds, 4 single bonds, and so if it's bonded 4 times singly, it has to be sp3 hybridized. So then let's look at this carbon, the one on the right. It has 4 bonds, like it should. 1, 2, 3, 4. But we notice it has a double bond to an oxygen. Anytime you see a double bond, you should automatically think sp2. So, what's another question I could ask you? Let's use purple for this. So, I want to ask you the number of sigma bonds. So, we have 1, 2, 3, 4, 5. Now, we have to remember one of these double bonds is actually a sigma bond. So there's 6 total sigma bonds. So then I can ask you the number of pi bonds. Well, there's only one double bond, and so there only has to be one, right? So I can ask you guys what's the hybridization of a central atom? How many bonds are in that atom? And so what I want you to do is I want you to do number 63, and this can be done for the Monday before Thanksgiving break. And what I want you to do, all I want you to do is to do the Lewis structure. I want you to do the hybridization scheme of the central atom, and then I want you to do the number of sigma and pi bonds. So instead of what it actually asks you to do, I don't want you to have to draw the bonding scheme or whatever. I just want you to do the Lewis structure. I want you to label all the bonds, and I want you to tell me what the hybridization is of the central atom. So, one more thing left to do. The molecular orbital theory. So, this is the most advanced bonding theory we will discuss. This is my favorite bonding theory. And what we're going to actually do is we're not going to talk about orbitals as we know of orbitals. We're going to make our own orbitals. And so, but we have to think about waves. Right? Because we said electrons behave as waves. Here is constructive interference. So what do we get? We get a bigger wave in sync. Waves can also do this. This is known as destructive interference. And we get nothing. It limits it out. So, what can we do? So, what we can do is these electrons lead to what's known as a bonding orbital. These electrons leads to what's known as an anti-bonding orbital. And so anti-bonding will be denoted with a star. So every time you see a star, you know it means anti-bonding. So, let's look at hydrogen. Let's look at hydrogen as an example. So, hydrogen, 1s. So what you do for the molecular orbitals is you draw the electron configuration, or the orbital diagram for your element that you want to do on each side. And so what you're going to do is then what you're going to do is you're going to make the molecule in the middle. There is a new orbital formed that's of lower energy than the old ones. There's one that is also of the higher energy. This is sigma 1s. This is sigma 1s, but we're going to put a star. So what we do is we make a bonding orbital, a molecular orbital, and an antibonding molecular orbital. And then what we do is we take the total number of electrons and we start filling them in again, according to off-ball principle, from the bottom to the top. And so we're going to put one here from the hydrogen on the left, we're going to put one here on the hydrogen on the right. That's all we can do. So then how in the world do we know that these things are actually going to bond? Well, we can calculate what's known as the bonding order, BO, the bond order. And the bond order is the number of electrons in, let's say, a bonding molecular orbital minus the number of electrons in a non-bonding molecular orbital, or an anti-bonding, molecular orbital, divided by 2. So, in the case of hydrogen, you have 2 electrons in a bonding orbital minus 0 electrons in the non-bonding orbital, divide that by 2, and you get 1. Any number greater than 1, a positive number, it will bond and it will be stable. So let's look at a different example. What this can do, again, it's all about predicting what will happen. So let's go and erase all this, because I'm going to look at a different compound and why a different compound doesn't form. So let's look at helium 2. So why don't we get He2? So helium looks like this. So let's go ahead and fill in, right? Because we have 4 total. So we just add 4, put 2 in the bottom, 2 in the antibonding. Let's go and erase this. That was a 2. So let's look. Number of electrons in bonding or molecular orbital, 2, minus number of electrons in the antibonding orbital, 2, divided by 2, you get 0 divided by 2, which is 0. If you get 0 or a negative number, there is no bonding that can occur. It's too unstable. And so what I want you to do for an assignment, this will be due the Monday after Thanksgiving. So the Monday after Thanksgiving is the 26th. So this will be due on November the 26th. But I want you to do a little bit of an exercise. And I want you to try it yourself. And if you have any questions, then please come see me. We'll talk about, in class, adding pi bonds to this. And again, use your book as well to help you out. I want you to tell me something. I want you to tell me, I'm going to give you 2 molecules. N2 plus, O2, and O2 2 minus. You have 3 molecules. I want you to tell me one. Which is more stable? And you tell stability of bonds by bond order number. The higher the bond order, the more stable a bond is. And then I want you to tell me if they're paramagnetic or diamagnetic. And so go ahead and try those. I understand that it might be a little stretch to do them, but I want you to try. If you need any help, feel free to please come see me. Good luck. This ends all of the videos that cover everything we've covered in class. If you need to, I would recommend looking over the videos, over things that as you study the ACS for your final. I would recommend looking over those videos again.